we're going to start off with any questions you may have.
Great. I don't have any questions so far. Just
Okay,
all good.
then we're going to do questions that I have. All right.
Cool.
So I'm going to change my share screen so that you're going to be looking through this Elmo here.
All right.
Let me make sure I got the Elmo up and running. And I don't. So I can't share that. It'll take a moment for it to turn on. It's a little slow, temperamental.
For sure.
Did you watch the inauguration this morning?
I sure did. Yeah, it was nice.
Yeah. I actually missed it because I thought that the swearing in was going to be at noon or 9 o'clock our time.
Yeah, it's like what is it, Eastern time?
Yeah, so I thought it was going to be 9 a.m. our time, but it turned out that the actual swearing in was earlier. So
Yeah.
I got there in time basically to see his speech and then to listen to Garth Brooks sing, which is nice.
Yeah. Cool.
And I don't know where you stand on all of this, but I'm pretty excited.
Yeah, I am too. Very excited.
It would be nice if everything could become more civil and we just have disagreements in the future.
Yeah, seriously.
Instead of fights.
Yeah, instead of deciding to stage, domestic terror attacks
Yeah.
on government buildings, might be a better call just to, talk to one another.
Yeah, and have disagreements. You don't have to.
Yeah, you don't have to agree,
You don't have to agree, but you do have to discuss things.
Yeah.
That's the way it is. That's how America works. Okay, so you can see here, I've written out some things from the textbook. And these are problems from the back of the book. They're the even numbered problems. And they're only the even numbered problems that aren't really, really, really long because I'm writing them out.
Right.
But this is a good start. I don't do the odd numbered ones because there are answers in the back of the book.
Right.
So I want to help you out with ones where there aren't answers and also give you what I would expect to see if this were a question on the test and the kind of things I would like to see generated as an answer. Okay.
Right.
And I should tell you that this is also a way that I like to study when I study material is, you know what? I didn't do my share screen, did I?
No, not quite.
So let me share this screen with you. I need to get to Zoom. So right now you're just looking at me.
Yeah.
Okay, so this is a problems written from the back of the book or back of the chapter.
Sure.
So I think this is a great way to study. Don't read the chapter because it's a waste of time. You don't know what's important. I mean, they do have bold words. They do have sections, but you really don't know what you're supposed to figure out until you get to the problems.
Yeah.
So if you go straight to the problems and you read something like this, you say to yourself, oh, I better find the section that talks about hypotheses, theories, and laws and figure out how to distinguish between the three.
Yeah.
Okay, so in general, and I have this written out somewhere from yesterday, so I'm just going to pull that out. This is kind of what I wrote down off the top of my head for these three different things. So in context here, state whether the following is a hypothesis, theory, or law of science. Global climate change is occurring because of human-generated carbon dioxide, and explain. So hypothesis is a simple explanation for some observation, like years ago when we first moved into this house, woke up one morning and there was condensation all over on the inside of the window in my son's room. And the interesting thing was that the condensation happened to be greater near his bed and less the farther away from his bed. So I asked him, look at that condensation pattern. There's more of it closer to you and less of it farther away. And he goes, well, that's because it's coming from me. So there's more of it closer to me and less of it farther away. And that was his hypothesis. And I said, well, how could you test that hypothesis? And that's the next step. You have to be able to test it. How could you test that hypothesis? He goes, well, I just sleep on the other side of the room and see if I get the opposite pattern.
Yeah, exactly.
So it has to be testable, and it has to be capable of being proven to be wrong. So if he had slept on the other side of the room, but saw the same pattern the previous night, then it wasn't because of him.
Right, falsifiable.
Right. So that's and we also call that the null hypothesis. And falsifiable is a great word. In fact, I'm going to write that in here.
Yeah, I'm already kind of usually like, because I took biology last semester, and then I'm an AR student, so I took chemistry right before. So usually I'm finding like a lot of the like chapter 1 stuff is like mostly kind of review, which is
That's
cool.
good. You actually should find the whole semester review.
Yeah.
We just may go into a little more detail.
Right.
Okay, so for a theory, it's basically a unifying body of facts. And it's usually you have an explanation for that body of facts. And I have mutable that you can change it depending on new facts. Like the theory of evolution has undergone many mutations as we find out more and more information. But the tenet, the basic theory of evolution, that you're passing along traits through hereditary means, that hasn't changed. And law is something that seems to be universal no matter what. So that objects of mass are attracted to one another seems to be universal, whether you're here or on Mars. And it's these universal things that really help us to do things like go to the moon or send a spaceship to Mars, because if we didn't have these universal laws, there's no knowing what would happen once a spaceship leaves Earth. So this is the kind of the difference. And when we talk about climate change, I think it's beyond the hypothesis, because it is a body of facts supporting a theory. But it's also not a law. We don't know that climate change occurs everywhere else in the universe. And specifically, this climate change is talking about climate change due to man-produced CO2, essentially. And well, that was my thought on that. Now, a person did ask, well, how come it's not really just a hypothesis? And I was thinking, that's kind of an interesting question. And the answer is, I'm not sure. I think that there's too much evidence to say that it's just a hypothesis anymore. There's a big body of evidence supporting it, so we call it a theory.
Right. And I don't know, the way I always think about it is the hypothesis is what you do before the experiment, saying this is why I think this happens. And then the theory is taking all of the data that you've collected through the experiment and then saying, based on the data, this is what I can infer.
Right. That's what a lot of people think. But on the other hand, when did the idea of man-made climate change really come to the fore? Probably about 20, 30 years ago.
Even I think
how long have you been, pardon me?
I said, I think even longer ago than that.
Possibly, but really to the forefront about 20, 30 years ago. But how long has climate change or changes in climates been studied? Long before someone proposed the idea that it's due to man. So sometimes you're just gathering evidence of different things and someone comes up with an idea. I don't know if you've ever read any of the Stephen Gould type stuff, but he came up with this idea called punctuated equilibrium for how evolution occurs.
Sure.
Basically, there's equilibrium, and then some extinction event occurs, and then you have a widening a proliferation of fauna.
Oh, right. Yeah. All the space gets like filled in, right?
Yeah.
All
So
this
all the
liquid.
different, yeah. So,
Like a
and then you get all sorts of different organisms.
Mhm.
But it only happens when you get rid of a bunch of organisms to make room for new ones.
Right. Yeah.
So once you get all that proliferation, then it kind of stays steady state until there's another extinction event.
Mhm.
All right. So let's go ahead and move on from that. Oops. And what I did on this here is, oh, here's someone else. Destiny is added. We'll wait for her. Assuming it is a her. All right, Destiny, welcome to the Zoom session. Alice will be adding here, and Jacoby is also here. And sorry, I didn't know that you were trying to get in, Destiny.
It's
I don't
okay.
know how long you were waiting.
Just a few minutes. It's fine.
We were talking about problems from the back of the book because Jacoby didn't have any questions. And so my default is to do problems from the back of the book and give explanations and to write stuff down that I would expect to see as part of your answer on an exam.
Okay.
Okay, so now that both of you here, Alice and Destiny are here, do you have any questions that you would like me to address before continuing with this? Alice? None? I think you're muted. You can just give me a
Sorry
shake.
about that.
I was gonna say, you could just give me a shake of the head. So,
Not at the moment. I was a little flustered. I couldn't get in, so I'll see if something surfaces for me.
okay.
But right now, I'll just watch what you're doing. Thank you.
So I was explaining, and I'll do this very briefly. I was explaining to Jacoby, I think a great way to study is to not read the chapter, but start doing problems from the back of the book. Because when you read a problem like this, number 2, you realize you better read about hypothesis theory and science. So when you go read about it, then you're actually looking for something and you'll learn it better than if you just read through it and you don't know whether it's important or not. So I call it active reading compared to passive reading. And I always learn better when I'm looking for something, trying to understand something instead of just reading through it. Okay, so here, number 4, if we take a look at that and we look at what is meant by the phrase green chemistry. So if we look at the book, we'll see that there's a whole bunch of different tenets of green chemistry. And so what would you want to write as an answer to something like this? If you have your book, you want to open it to page, so it's really towards the beginning of the chapter. I have it right here. This is page 5, and this is about green chemistry. And you can see right here, Paul Anastas and John Warner created or stated the principles of green chemistry. Now, I would hate to see an answer like that on an exam, and I would hate to have to memorize that answer. So let's try to summarize what these tenets are for green chemistry. Prevent waste is better than to treat it or clean it up. So I think you can summarize that with prevent waste. Pharmaceuticals are producing large numbers with chemical processes. They should be designed to maximize all the materials in the final products. So do you see how that's part of preventing waste? So I don't think that's a new idea. It's a more specific example of preventing waste. Designed to use and generate substances that produce little or no toxicity. Now that seems to be different than producing waste. Not all waste is toxic, but you want to reduce the amount of toxicity. Products designed to function effectively while still reducing toxicity. that seems to still be part of the reducing toxicity. There is the little nugget of you want it to work and not be toxic, but that kind of goes without saying, right? You're not going to make something that's not toxic and it doesn't work, if that makes any sense. Let's move along here. Energy requirements should be minimized. And they should be conducted at ambient temperature and pressure. So ambient temperature means you don't want to have to heat it up because that requires energy, or cool it down because you're going to have to require energy to cool it. Raw materials should be renewable. That seems to be a new idea. At the end of their function, they do not persist in the environment or break down into dangerous products. That seems to go back to the toxicity thing and the waste thing. And chosen to minimize potential for chemical accidents. So that's a safety issue. So if you had to decide what the big parts of green chemistry are, to me, it seems like they are, you want to prevent waste, reduce toxicity, minimize energy use, and you could write energy consumption, but that has far more letters than use, so I'm going to write use. Let's see, I have to go back and refer to what I read. Use renewable materials. And safety. And the safety part covers the safety in the manufacturing of the material. It includes the use of the material and what happens with the material afterwards. But this is a nice summary, I think, of what we're talking about with green chemistry. Does that kind of make sense? So this is the kind of answer I would kind of expect on a test. I wouldn't expect you to memorize all of those different things. That would be silly of me. But these basic fundamental ideas, I think, are important. So are you with me or are you against me? All right. You know, against me like a pirate. Are you with me or are you against me? If you're with me, you're supposed to do this with your arms. We're with you, Tony. Arr. We can do the patch. All right. So that's my pirate stick. Okay, so let's go to the next question here. So wait, give the name of each of the following elements. So before I talk about this, I do want to talk about the periodic table, because for the exams and quizzes, you want to be aware of the names and symbols of the elements that we're going to be using in this class quite a bit. You don't want to have to look at a problem and go, oh, geez, what does that symbol mean? You just want to know it. So I want to provide you with the symbols that you should know like that very soon. Fair enough? Okay. So here's my periodic table. And let's see if I can zoom out and see most of it. Actually, I don't think I'll be able to. So what I'm going to do is I'm going to change my screen share. And I'm going to type in periodic table. Actually, I'm going to type in web elements. Okay, so here is a periodic table of the elements, and let me see if I can make everything a little smaller. Okay, so we can see quite a few of the elements here. And the first thing I want you to notice is that over here on the left, we have an H, and there's a 1 at the top of it. And if I click on this symbol here, we're going to see the same thing right here. But the H is on the bottom. It really should be at the top. And so I'm going to go back to the printable table. I've never been there. I want to take a look at that now. Oh, that didn't do anything for me. Okay, so if you look at that H, there's a 1 at the top. If you look at helium, there's a 2 at the top. Lithium, there's a 3 at the top. So if you imagine these elements are written in numerical order, 1, 2, 3, 4. Even here where you have number 56 and right next to it you have number 71, 56 actually jumps down here to 57. Then you go across to 70, then back up to 71. You should learn the names of the first 40 so that if you're given the symbol, you can write out the name, or if you're given the name, you can write out the symbol. For instance, if you were given the name iron, you should know that the symbol is not IR because iron is spelled IRON. The symbol is FE. The first letter of a 2-letter symbol is always uppercase, and the second is always lowercase. So when I say uppercase and lowercase, let me give you an example, and I'm going to switch to the next screen, or to a different share screen. So let's say that, and I need to reverse this. This will just take a moment. How did my screen get turned around, and how do I switch it back? Let me give this a try. No, that didn't do it. Here we go. Oh, okay. So this is a old fart time. You see how my screen's upside down? It's not because my screen's upside down. It's because my paper's upside down. So what you've seen is a senior moment captured on video.
Yeah.
And that was quite interesting. So let's take a look at copper. Copper has the symbol Cu. If you write it like this, this is actually copper and uranium. Manganese is Mn. This is not allowed. So there are differences in the way that letters look between uppercase and lowercase. The first letter is always uppercase, and the second is always lowercase. And I don't mean just shorter, I mean lowercase. Okay? So anything like that would be construed as being wrong. Sometimes you can get away with it. This is cobalt, and if you drew that as an uppercase, I wouldn't know it because you made it short. So you want to know the first 40 based on the number at the top. And then you want to know the following elements. I'm just going to write them out by symbol You should learn these names and symbols. I also want to tell you that you do not need to know which number it is. So you don't need to know that magnesium is number 12, because on an exam, I'll give you a periodic table that'll have 12 at the top. It'll have the symbol Mg, but it will not have the name magnesium. So I'll give you the periodic table. You just need to know what that is. Okay, so the first 40, and then beyond the first 40, I would like you to know silver. I would like you to know tin. I should actually do it this way because they're kind of in the same period. I would like you to know iodine. And I would like you to know xenon. Now you might say, well, why is he saying iodine? That's kind of silly. It's iodine. Well, if this is iodine, then this is bromine, this is chlorine, and this is fluorine. But if this is fluorine and chlorine and bromine, then this is iodine. So that's why I say iodine. You've got 3 against 1. So the 3 win and it becomes iodine. If you say iodine, I won't be bothered by it. Okay, from the next period, we want cesium, barium, lanthanum, platinum, gold, mercury, lead, bismuth, polonium, and radon. The next period, you want francium, radium, and then from the place below, you want the following. You want this one definitely. Does anyone know what that one is? It's Humboldt County's element. You know how you have a state bird, a county bird? This is the Humboldt County element. It's called erbium. Get it? Erbium? Humboldt? Okay. You don't need to know that one.
Knee slapper.
This one you should learn just because it sounds so cool. Protactinium. But you don't need to know it. You should know uranium. You should know plutonium. You should know americium. And so these, in addition to the first 40, you should know the name if given the symbol, or be able to come up with the symbol if given the name. And a lot of them are weird, like, Ag is silver. What's up with that? Tin is SN, doesn't start with a T. Well, a lot of these symbols come from the Latin name.
Latin.
Yeah, it's just like a potassium, as we can see here, has the symbol K. Its Latin name is callum, and callum starts with a K. Sodium is natrium. Okay, so I'd like you to know the first 40 plus these, where if you're given a symbol, you can write the name, or if you're given the name, you can write the symbol. Is there anything unclear about that? If so, please let me know. Okay, so let's go ahead and these problems here. So what's Mn?
Manganese.
Nope. Magnesium.
Mm,
Oh, excuse me,
Oh.
manganese. Well, you're right. Manganese. Magnesium is Mg.
Mg.
You're absolutely right. What is Cu?
Copper.
Okay, say it like you're from Boston.
Kappa.
Copper.
Kappa.
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 That's
Don't
not the same
understand.
word, is it? That's policeman, I think.
How about Na?
That's sodium.
Sodium.
Correct. Sodium. How about Br?
Bromine.
Bromine.
Bromine. How about Z or Xe?
Xenon.
Xenon, Princess Warrior, right? What's her name? Xenon? No, she was Xena.
Xena.
She was
Xena.
Xena. And
I'm not
Effie,
sure everybody's gonna know that. That's kind of a
Oh.
that's a dater.
It's an old one.
hold on, I am old. I'm working on my sixth
Me,
grade.
I get it. I get it.
How about
I knew it. So
Fe?
Iron.
iron.
Yes, and it's not spelled like iron. That's how you spell iron. It's spelled iron. So make sure you spell it correctly. There are some tricky ones here to spell. I'll give you an example. Fluorine. So go ahead and try and spell that one out.
Fluorine.
Now, this is how most people spell it.
Mm-hmm.
Now, read it. Actually read it.
Flowering.
Flowering.
Mm-hmm.
So that is not the spelling. That's the spelling. Okay? So don't write flowering. I'm just going to count it wrong. Okay? And as far as spelling goes, if I know how to spell it, you should know how to spell it. And the reason I say that is because my spelling abilities are horrible. And if yours are worse than mine, you should be ashamed, because I'm ashamed of my spelling. Okay. So any questions about number 8? Okay, let's move on. Okay, so this is on page 22. Let's give the symbols for each of the following. So silver is one of those ones that doesn't follow suit with the name.
Mm-hmm.
It's Ag. I honestly don't know the Latin name from which that derives. Aluminum, notice that there is no I between the N and the U. If you were raised in Europe, you might call this aluminium. And that's fine if you were raised in Europe. But if you weren't, I expect you to say aluminum. So Al, what you don't want to do with something like this is that, because that looks like an uppercase L.
Mm-hmm.
So if you want to put the little lick at the end, you can do that, but just, make it slight like that or something like that, rounded like they do with a typewriter. Don't put a rough or abrupt edge on it. Fair enough? I admit that when you do something like this, you don't know whether that's an I or not. So the tendency is if you're going to use an I for iodine, you write the crossbars on it.
Mhm.
Okay. C, plutonium. D, tin. That's another odd one. I do know the Latin name for this. It's stannous or stannic, depending on the type of tin. Technetium is TC. And krypton, an uppercase K and a lowercase r. And here I'm going to give you another example of that is not correct. Fair enough? Okay, moving along. In each of the following pairs, decide which is an element and which is a compound. So how do we tackle this? And the answer is very simple. If it's on the periodic table in a box, it is a symbol of an element. If it is, if the name matches a symbol of an element, like copper matches Cu, then it is an element. However, if the formula, this is called a formula right here, if the formula is comprised of more than one element, then it is a compound. If the name is comprised of more than just one element's name and it has other stuff associated with it, it is a compound. And if the name cannot be found as the name of an element on the periodic table, given the choices here, it's a compound. So based on this, I'm not going to write this down. Platinum is an element. This compound here, or this formula here, is a compound. Copper is an element. Copper 2 oxide, that's the way you say this, copper 2 oxide. This is a compound. Silicon, which you can find on the periodic table, is an element, and sand is a compound. Any questions about how you would distinguish those? Okay, let's move along. Let's back it up. What does this formula indicate for the number of platinum atoms in this formula? How many platinum atoms?
1,
1, that's correct. How many nitrogen atoms?
2,
2 is correct. How many chlorine atoms?
2,
2. And how many hydrogen atoms?
6.
6. This is a shortcut way of writing this. So when you have 2 of the same thing, normally you'll put that in parentheses with the 2 on the outside if there's more than one element in the thing. When there's only one element in the thing, like this, you just put a 2 after the symbol. And this is short for the following. So you could write all those hydrogens out. Chemists figured out a long time ago that they don't want to do this. They don't want to do this. And so you'll write a formula out this way. Now, the reason this formula is written this way is because in this particular compound, there will be 2 NH3 units, which are put together in a particular way, the same way. And since there's 2 of those and you have 3 hydrogens attached to 1 nitrogen, you write it together. It gives you a little bit of information about how things are attached. So any questions about what this and this and this mean? Okay. So let's take a look at this one. You're actually going to do this. You're not going to do this lab. It's one of the ones that we normally do in a face-to-face setting. But it's too dangerous for you to do at home. So I do the lab. There's a videotape of me doing it. You watch it and you take the information and work it up. So I'm going to give you a moment to read through this. And while you're reading through this, let me give you some background music. Okay, are you ready? Did that one date me too?
No, it's still around.
But Alex Trebek, oh, he has passed.
Just barely.
Just barely. Well, how can you, what's unbarely passed?
A decade or 2, I don't know.
Oh, you're talking time-wise.
Yeah.
Okay, so here a sample of the compound magnesium oxide. And notice this has 2 parts to the name. So it's probably not just an element, and they do use the phrase or the word compound. Is synthesized as follows: 60 grams of magnesium is burned, produces 100 grams of magnesium oxide, indicating that the magnesium combined with 40 grams of oxygen in the air. So here there's a whole lot of information. It basically tells us that 60 grams of magnesium is going to give us 100 grams of magnesium oxide. And you might say, well, why is he putting an equal sign in there? And the answer is simple. If I wrote 20 slices of bread, I might write that that's going to equal 10 sandwiches when I'm done. Now, I'm not telling you that 10 sandwiches are equal to 20 slices. I'm telling you that I'll need 20 slices to make 10 sandwiches. Are you with me there?
Yeah.
So that equal sign is kind of like writing out a recipe saying, I need this equals this for my recipe.
Mhm.
And so this equals 40 grams of oxygen.
Huh.
Okay. And they tell us that 40 grams of oxygen. Now they say if 30 grams of magnesium had been used, what mass of oxygen would have been combined with it? Let me show you how to do this problem. So we know that we're going to start with 30 grams of oxygen. And we know that if we start with 60 grams, we'll end up with 100 grams here. So since this is half of that, we should end up with 50 grams of magnesium oxide, correct?
Mhm.
It's a proportionality problem. And here, what mass of oxygen would have combined with it? Well, naturally, here, if we add half of this, we'd make half of this, we need half the oxygen.
Mhm.
But we can actually make this a mathematical problem instead of a thought problem. And here's how it looks. You'll notice that I took 40 grams of oxygen, put it on top, 60 grams, put it on the bottom. And the reason I can do this is because 40 grams of oxygen equals 60 grams of magnesium, which means that 1 divided by the other is 1. I'm basically multiplying this by 1. So this is something you're going to be learning in the second half of the chapter. It's called a dimensional analysis or a conversion factor method. And we'll be using a lot of this in the later chapters. This is called a number, this is called a unit, and this is called a label. In this case, this label is the symbol of an element. Okay, so does everyone understand how to make sense of this one? Where we basically say that if we use half the amount of magnesium, we would need half the mass of oxygen. Are we good on that?
Yeah.
I'm going to do something really quick here. Where's my Zoom settings? Oh, I put them up here. Participants, that's what I want. So here's what we're going to practice doing is when I ask you a question, I go, are we good? You are going to give me a thumbs up. So just to make sure you know how to give me a thumbs up, I want you to open your participant list. And at the bottom of that participant list, you should find choices like thumbs up, thumbs down. I'm not sure what else they have. Maybe raised hand. And then there's more. And in the more part, you've got all sorts of different things like clapping hands, I think, and so forth. So what I want you to do is give me a thumbs up.
It's not there for me. It's under reactions. It's not under participant. It's a
React?
different icon. Yeah. It's there.
It's not under participants? What are you using?
No,
Are you clicking
I'm
the up
using
arrow?
the. I have I downloaded a new version of Zoom just 3 days ago, so I assume it's the newest. There's 5 icons on the bottom, and the last one is reactions.
Right.
And
So under
under that,
reactions,
I have a
you have a
thumbs up.
thumbs up?
Yep.
Okay, so then you're just gonna go to reactions.
That's how I did it too. But you can also get to it, at least for me, when I click on participants, there's that little up arrow, which doesn't do anything. But then when you click that, you can click more next to your name.
Oh, really? When I go to participants and I click the arrow, it says invite.
Right. Yeah. That's what I get too.
I don't know what
But
the
then
hell.
if you physically if you click the participants button, like that little 2 people or whatever.
Yeah, I just get a list of the participants, but I don't have the right to,
Me too.
I can't give you a thumbs up or thumbs down because I guess I'm the host.
Mm,
I have to do it this way.
yeah.
So yeah, they don't give hosts a lot of choice. It says you can now, it does say you can now send nonverbal feedback, yes, go faster, etc., from reactions on the toolbar.
Mhm.
And I don't
Like
have
that.
I don't have reactions on my toolbar.
Hmm.
So once again, the host is not allowed to do any of that. That's a bummer. All right. So now let's address this last issue. What law of chemistry is used in solving this problem? Does anyone know? It is the law of the conservation of
Energy.
matter.
Oh, matter.
Some people don't call it this. They call it the law of the conservation of mass.
Mm.
And you can see we are working with mass numbers or mass values. So either way of saying it is correct in my opinion, law of the conservation of matter or the law of the conservation of mass. And so here you can even see that in this particular reaction, because here you're combining 40 grams of oxygen and 60 grams of magnesium. So if you're not going to lose any mass, your product should have 100 grams.
100 grams.
Are you with me there?
Yes.
No. Okay. Jacoby's giving me the thumbs up, but what are you supposed to do? We're with you. So if we're really going to be participants, you would say, we're with you. Let's board the next problem, Tony. All right. In each case, decide if the change is a chemical or physical change. So before we do this one, what is the hallmark of a chemical change compared to that of a physical change? And the answer is simple. In a chemical change, you're changing the formula. So a symbol of an element is a formula. And so when you say Cu for copper, that's the formula of copper metal. If you oxidize copper and make copper 2 oxide, the formula is Cu uppercase O. That's the formula. So when you change from one formula to another formula, that's a chemical change. Anything else is physical. So for instance, let me show you an example of a physical change. Does anyone know what this symbol represents?
Water.
Or what this formula represents?
Yeah, that's the hydrogen monoxide.
Yes, a very dangerous, one of the most dangerous compounds in the world.
Yeah.
Causes hundreds of deaths every year.
Mhm.
Teaspoon of it can kill you.
Yep.
It should probably be outlawed due to its danger, and it's toxic. Too
Yep.
much of it will kill you.
Yep.
And too little.
And too little. Okay, so the proper way to say this formula would be H2O. You would not want to say water. Now, if I did this, you could say water because the L represents liquid. The arrow represents change. So the H2O liquid is changing into, and here I'm going to make it H2O solid. So this is water freezing into ice. This is a physical change because the formula does not change. However, you can take H2O and under the right circumstances, you can do this. You can separate the elements from one another and you can make hydrogen gas and oxygen gas. The G means gas. This is not balanced. It's not meant to be balanced. I just wanted to show you that this is a chemical change. And the reason it's a chemical change is because the formula changes. Fair enough?
Yep.
Now, here's where things often get confusing for people. Here, if the liquid is turning into the gas, isn't that a physical change? And the answer is absolutely, it's a physical change. Yep. But when we ask, is it physical or chemical, we're really asking, does the formula change? Mm-hmm. So I want to make that as clear as possible. When we're asking chemical or physical, we're really asking, does the formula change? Because honestly, most chemical changes involve a physical change. All right. So another way to think about these, though, is this. I'm going to go back to here. Is it easy to undo the freezing of water? Yeah, just take a piece of ice cube and leave it on the table. It'll melt. Is it easy to undo this? And the answer is absolutely. All you do is light it and you'll get the water back. Okay. But on the other hand, is it pretty easy to take water and freeze it? I'd say, yeah, all you need is a freezer. I'm considering the conditions that you have in a normal household in the United States, not say a place where electricity is hard to come by, okay? Is it easy to separate water into hydrogen gas and oxygen gas? And the answer is no. This is hard to do. The point I'm trying to make is that oftentimes when you look at physical properties, they're easy to change and they're easy to change back. And for chemical properties, they're harder to change or harder to change back. So that's another way to try to decide if you're looking at a chemical versus a chemical change versus a physical change, how easy is it to reverse? Now, it's not always perfect. For instance, if you take a piece of iron and cut it in two, how easy is it to put them back together? Well, it's really hard to melt it, but you could do it. So it's not a perfect rubric for separating things out, but it's something that you can kind of go to once in a while, okay? So chemical change in formula, or hard to reverse or hard to do in the first place. So let's take a look at the first one. A cup of household bleach changes the color of your favorite teacher from purple to pink. That's definitely a physical change, right? Purple to pink. Mm-hmm. But is it now pink because the formula of some compound has changed on your shirt? Well, we don't know because we don't have the formula for pink or the formula for purple. So we're going to rely on, is it going to be easy to take that shirt and turn it back to purple? What do you think? How do you unbleach a shirt?
You just dye it, yeah.
That's not unbleaching it. I said, how do you unbleach it? Not how do you make it purple again?
Can't really
How
get
do you
bleach out.
unbleach it?
That would be tough.
Can't really unbleach stuff.
You would expect that if it were easy to do, then the guy who sells you sham wow would be selling you this. You got to buy this unbleached. It's great. Not only will we sell you this, but we'll sell you another one for free. And you only have to pay for shipping charges. You with me?
Mhm.
There is no unbleached product out there because it's hard to do. So we're going to have to call this a chemical change. Does that make sense?
Mhm.
Okay, how about this one? Water vapor in your exhaled breath condenses in the air on a cold day.
Physical. Because you're just changing the state of matter.
You're
Right.
just changing the state of matter. So the vapor that comes out is gaseous, and because it's cool, it condenses. What happens as the day warms up?
Goes back to liquid.
Turns back into a gas.
Yeah.
Well, if it gets hot enough.
Yeah. Okay, so this is a physical change. Plants use carbon dioxide from the air to make sugar. This one is interesting because we can actually say, hey, look at that. Carbon dioxide, compound or element?
Compound.
Compound.
Compound, because it has carbon with another element there, oxygen. That's got to be a compound. From the air to make sugar. Do we think sugar's an element? Did you see the symbol for sugar on the periodic table?
Mhm.
Compound.
I think it's, isn't it SU? Oh, there's no SU on the periodic table. There's no, okay. So this is a compound. They have different names. What does that make you think?
Different compound.
Chemical. Yeah.
Different formulas. Therefore, this is a chemical change.
Mhm.
Okay. Butter melts when placed in the sun. Now, I could see this being answered two ways. How could we call this a physical change?
I mean, it's just, again, like state of matter, pretty much switching
Yeah,
from
you
solid to
remove it
liquid.
from the sun and it solidifies, right?
Mhm.
How might you call it a chemical change?
Oh.
Well, I know this for a fact. If you leave it out in the sun for too long and you taste it, it tastes different.
Rancid.
Yeah.
Now, what has happened there is that the sunlight has provided energy to allow for the oxidation of some of the things in butter.
Mhm.
And when it oxidizes, it has a particular taste that we call rancid. So it depends on how long you place it in the sun. And so, this might be subject to how you understand what's going on and how long. But if you are talking about just placing it in the sun and then taking it right out, a physical change. Are we good to go? This is a thumbs up time. Good, Destiny?
Yeah. I
Oh.
accidentally closed the tab
Oh, that's fine.
minimized it.
Okay, let's look at number 18 here. I hope you guys are finding this useful. I like this a lot better than going through lecture, looking at problems and trying to explain what's going on. Okay. Which part of the description of a compound or element refers to its physical properties and which to its chemical properties? So here I am actually going to take out a piece of paper and make a list. So we're taking a look here at A, and I'm going to write chemical and physical. So I'm going to start. Calcium carbonate, chemical. Because it's the formula of a compound. And to change it would be to change it chemically. So this is a chemical property when we say calcium carbonate. Physical, white. Solid. The reason I have them separate rather than together, as they are up here, is because the color is regardless of the state. You can have a white liquid. Milk comes to mind. With a density of 2.71 grams per centimeter cubed, the density is a physical property. And here, you might not know that offhand, but when you think about the density of something, is that something that that the whole thing has? I mean, that is to say, does all calcium carbonate have that particular density? Is that something that you could figure out? And this is another way to figure out chemical versus physical is that something you could figure out without changing it into something else? So can you get the density of an object without changing it into a different material? And the answer is absolutely. So density is physical, reacts readily with an acid, reacts with acid to produce gaseous carbon dioxide. So I'm going to put gaseous and then carbon dioxide. Are there any questions as to why I put what where? You could actually write reacts with acid to produce. These are usually key words that tell you it's a chemical change, react and produce. Fair enough? In fact, for chemical reactions, this stuff that you start with on the left are called reactants. They react together to produce the products. So these are key words that usually tell you you have a chemical reaction. Okay, how about letter B? Gray powdered zinc metal reacts with purple iodine. So I'm going to make another list: chemical and physical. So I'm going to put gray over here, powdered over here, zinc over here. What about metal? Do we want to call that a physical or a chemical property? And it's kind of a toss-up, I'll be honest with you, because metals react in particular ways that non-metals don't. So you could call that a chemical property, but on the other hand, you can determine whether something is a metal without changing it into something else.
Mhm.
So I'm going to put metal actually in both places.
Yeah.
It really depends. Fair enough?
Yep.
Okay. Reacts with purple, iodine. Oh, he's at it again. He just said iodine. How many of you are now going to start saying iodine instead of iodine? Anyone?
I
No.
think there's just some times where if someone says a word like wrong enough and it becomes popular enough, it kind of like switches to being correct.
Yeah, that hasn't happened with iodine. I'm trying to change the world and it hasn't gone back to iodine. Okay. White compound, white, and then compound. Fair enough?
Mhm.
Okay, excellent. A solar panel is pictured. I did not draw the picture, as you can clearly not see it. I don't even know if that's a thing. Here's the solar panel from the book. When light shines on the panel, it generates an electrical current that can be used to recharge the batteries in an electric car. What types of energy are involved in the setup? So there are two major types of energy. There's kinetic, which is basically energy associated with motion. And there's potential, which is energy that is stored somehow. The major types of kinetic energy are translation. So that would be like a ball moving from one place to another and so forth and so on. Water flowing down a stream. Those are both translation. There's heat. Heat is kinetic energy, and heat is basically demonstrated in a number of different ways, but at the very initial part, it's the vibration of atoms. So if you don't have any vibration in your atoms, there's no heat. Once you add a little bit of heat, they vibrate. Once you add more heat, they vibrate enough where the atoms can move relative to one another, and then you call that a liquid. And then if you heat it up even more, instead of moving relative to one another, they'll actually fly apart. That's called a gas. That's kinetic energy. Sound is kinetic energy. And you might think, well, isn't sound just particles moving in the air? And the answer is no, they're not just particles moving in the air. Sound is produced by waves. So imagine if you have a rope attached between 2 points and you take one side of the rope and you whip it and it goes to the other side. When the rope is done moving, has the rope moved? And the answer is no, it's still where it was. But have you made energy move down the rope? And the answer is, well, stick your face in front of the rope on this end and see what happens. I guarantee you'll get slapped and you'll know there's energy in that wave. So with sound, you're actually pulsing the air and you're not moving it. So this is why it's considered to be different than translation. And other evidence to show you that sound is not moving the air is that someone like me who's been talking for the last hour, I would have definitely shoved all of the air away from me and I should have suffocated and you would be much happier by now. You with me? Capiche?
Capiche.
Okay. So sound is different than translation. And last, there's electricity or electric current. Same thing. And this is electrons moving, but it's different than translation in this fact, that when you have electrons moving, when one electron moves to one spot, another electron fills its spot. And so you have all of these electrons moving like musical chairs. Only the difference is there is a chair for every electron. So when those electrons are moving from chair to chair, you have an electrical current. And when the electrical current stops, the electrons all stay in their particular chair. So those are kinetic energy. Potential energy, we have a spring and it might be compressed or it might be stretched. A rubber band stretched out would be a stretched spring. You have potential energy due to position and gravity. In a classroom setting, what I'll usually do is I'll walk around the room and I will hold a book over someone's head and say, this book has potential energy. And then I will raise the book to 2 feet above the person's head. And I'll say, and now I'm putting kinetic energy into the book because I'm moving it. And then I'll stop the book at a much higher height above the person's head. And I'll say, and now I have more potential energy because we know if we drop this book, it's really going to hurt. And I've just turned kinetic energy into potential. So an important aspect is you can turn kinetic into potential and potential into kinetic. And then the last thing I do with the book is I say, and I've never dropped the books yet, but there's always going to be a first. So these are the things you miss when it's not face to face. Okay. So position and gravity, does everyone understand that? We good? There is also chemical potential. And it's basically stored in the bonds. So you have probably heard of dynamite. Dynamite has a lot of chemical potential because of the bonds. Something similar to dynamite is nitroglycerin. It has a lot of chemical potential due to the bonds. You may have also heard of TNT, another explosive. It has chemical potential due to the bonds. You may have heard of something called ATP, adenosine triphosphate. It's considered to be the energy molecule in biology. Why does it have chemical potential? Because of the chemical bonds. Okay, and then one more stored potential energy is electrostatic. So this is due to having charges. When you have a positive charge and a negative charge, they are attracted to one another. And if you keep them apart, they're like, they have a potential, because once you let them go, they'll come together. So electrostatic is a separation of charge, but they stay separated. And usually when we talk about electrostatic, what is causing the different amounts of charge? And the answer is different amounts of electrons. So back to this question here. When light shines on the panel, it generates an electrical current. So here we can say, okay, electrical current, that's going to be a type of energy, and it's kinetic energy. Recharge the batteries in an electric car. So batteries are definitely stored energy due to chemical bonds. And then there's light. Now, I have read that some people say that, well, light is not energy. And the reason is because it doesn't have mass. And I have to disagree with that. Just because something doesn't have mass doesn't mean it doesn't have energy. Because does it take energy to melt the butter? Yeah. Will light melt the butter? Yeah. Light has to have energy. So we have to decide, do we think light fits in the kinetic energy camp or the potential energy camp? And I think it's got to be called kinetic energy because light is moving from one place to another. You can't store light in a box. I mean, it almost sounds like a Saturday Night Live skit, light in a box. Okay. Any questions here about what parts of this would be considered to be kinetic and which parts would be considered to be potential? Battery, potential. Electrical current, kinetic. Light, kinetic. And in more particularly, the batteries would be chemical potential. Okay? All right, so we've reached the end of our time for today, 11:15. I'm going to continue on with some more problems from the end of this chapter. But I also want to point out something to you for this chapter. So here it seems to end on 27, but there is a second part to this chapter, the tools of quantitative chemistry. This is the section that is harder for students to grasp. We're going to be going over units of measurement, making measurements, and so forth. We will talk a little bit about this tomorrow for our measurements lab. We'll look at the math of chemistry, problem solving, dimensional analysis, arithmetic. The math of chemistry also involves something called significant figures. And I'm going to give you rules for knowing whether a number in a presented quantity is significant or not, or whether a number in a calculated quantity is significant or not. We have rules for that. There are reasons for the rules. Usually I don't spend time giving you the reason for the rule. I just tell you the rule and I tell you, I don't care if you like it, just memorize it. So we'll go over some of that. And I'm hoping to spend most of the time Friday on this type of material. All right. Does anyone have any questions before we terminate this session? All right. Okay. Yes, Alice, you're on mute, by the way.
I was just curious, tomorrow's Zoom time, could you talk a little bit more about like how that's gonna pertain to the lab versus like how you intend to use that time
Well,
specifically?
I'm going to post the lab a little bit later today.
Okay.
What I'm going to do is I'm going to talk about how to make measurements. I do believe that in the write-up of the lab, I tell you how to measure things, but I'll talk about it a little more just to give you, sometimes, reading it is not as good as hearing about it and seeing an example. For instance, if I were to show you that I wanted to measure the width of, can you see what I have here? It's a little piece of sandpaper. But if I wanted you to measure the width of this, I can show you by zooming in. How we could measure it. And do you see here how I'm trying to put one edge right at the 9?
Yeah.
Okay, so here it's going to the 10, that's 1 centimeter. Going to the 11, that's 2 centimeters. And if it went to the 12, it'd be 3 centimeters, but it doesn't make it there. So then we have to break it down, and it's going to be 2.5
9.
if it made it to right here, but it actually goes past that. So this is 2.6, 2.7, 2.8, but it doesn't make it to 2.9. And it's my responsibility to make an educated guess as to how far past 2.8 centimeters it makes. To me, it looks like it's almost all the way, but not quite. So I'm going to call that 2.88 centimeters. That would be the proper way to measure this. Now, if you said, no, it's 2.89 centimeters, I'd say, we agree. And the reason is because 2.88 and 2.89, the last digit is supposed to be your educated guess. In fact, if someone said 2.87, I'd say, fine, we all agree. But if you told me that that was 2.82, I'd say you need to check yourself and try again. So that's what I plan to do tomorrow for the measurements lab, is kind of give you some examples of measuring things. Does that make any sense, Alice?
It does. I was just curious. It's best for me to have the kind like the lab material to read like
Yep.
as early as possible, because then I can be prepared with the materials and such. So
It won't be posted until later today because of all the Zoom sessions and so forth and so on.
right.
Plus, there's some
Okay.
things I need to clean up for everything
Yeah. Yeah.
from last semester. All righty then. I'll try and get that done as soon as I can, though.
Okay, thank you.
All right. So the last thing at the end of every Zoom session, you're supposed to say goodbye to everybody.
Bye-bye.
So goodbye.
Yes.
Wait, I have a quick question.
Yes,
Do you post these recordings?
they are posted in Q&A.
Okay, I just wanted, because I saw that it was recording. I can't make it to like every day's session. But
So
I
let me show you something very quickly.
okay.
I don't know if I can do it quickly, but I'm going to give it a try. So let me close this Jeopardy thing. So if I go to the dashboard here and I go to the class, at the very bottom, module 1, I've got this Q&A.
Okay.
So if I link here, these are in YouTube. And you'll see that I have three videos posted, one from the morning from yesterday, one from the afternoon, and one from the evening.
Okay.
So I'm going to post this in the same place, only instead of saying Chem 1A morning 01/19/21, it's going to say Chem 1A morning 01/20/21.
Okay.
Okay.
Okay. Perfect.
All right. It's a good question. We'll hopefully see you again soon.
All right. Bye.
Bye-bye. Bye, everyone.